Hi guys! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about hydraulics. So, ngayon guys, ipakita natin itong ating first sample problem. In the problem, meron tayo ditong tube that is filled with mercury at 20 degrees Celsius, and we are required to find the force applied when the mercury level rises 15 centimeter above the base of the piston. We will be assuming that the specific weight of the mercury at 20 degrees Celsius to be equal to 13.55. So, ipakita natin ngayon guys itong ating figure. So, in the figure, meron tayo ditong cylinder, and inside the cylinder, we have, a piston whose weight is W. The cylinder has a diameter of 20 centimeter. And is attached to this tubing whose diameter is 1.0 centimeter. So initially, there is a difference in the elevation of the mercury from the base of the piston equal to 2.5 centimeters. So the problem dito is that when there is a force P applied or a force F applied at the top of the piston, the mercury rises a total elevation of 15 centimeters above the base of the piston, and we are required to find for the magnitude of that F that will cause that elevation to change from 2.5 to 15. Para maunawaan natin siguro yung scenario guys, ay ipakita natin ano ba yung mangyayari kapag in-apply natin ng force F itong piston at tumaas ngayon itong ating mercury from 2.5 to 15 mula dito sa base of the piston. And this is what will happen. Let us see the animation. So as F is applied, the elevation of the mercury inside the tubing rises to a height of 15 centimeters. So in this case, we will be required to find for this F. What is the magnitude of this F that have caused this elevation to rise from 2.5 to 15 centimeters. So, para maunawaan natin guys yung scenario, siguro mas maganda kung ibalik natin uli yung initial condition at i-analyze natin yung sistema in its initial condition. Let us bring back the illustration. Here's the case where there is no force applied yet on the piston. There is a difference in the elevation between the surface of the mercury and the bottom of the piston, and the height is 2.5. So we know that we're going to apply the principles of Pascal's law. We would expect that at the bottom or at the base of the piston there will be a hydrostatic force that would be acting, and let us imagine that that hydrostatic force or the pressure that would be acting, the pressure that would be acting here be equal to P sub 1. Similarly, on the same level of the mercury at this point, so we will expect that there will also be equal to, or there will also be a pressure whose magnitude is equal to P sub 1. And if we're going to apply the principle of the Pascal's law, na alam natin na on the same horizontal level of the liquid, the pressure is the same. Hence, asahan natin na yung pressure dito ay equal sa pressure dito. Kaya kung i-apply natin yan, ipapakita natin yan, then the two pressures are equal. Pero ano ba itong pressure dito sa ilalim ng piston? We expect that the pressure developed at the bottom of the pressure is the ratio of the weight of the piston to the cross-sectional area of the cylinder. So this is equal to the ratio of the weight over the cross-sectional area. Let us imagine here that A sub 1 is the cross-sectional area of the piston. And this will be equal to the pressure at this point, which can be computed by the height of the mercury and the unit weight, which is equal to the product of the unit weight of the mercury multiplied by that height of, or that difference in elevation between this point and the liquid surface. So from this equation, okay, we can express the weight of the piston W expressed in terms of A sub 1, that of the unit weight of the mercury, and this height of the mercury, or the difference in elevation between this mercury and the base of the piston, represented here by H sub 1. So that our W will be equal to gamma times H sub 1 multiplied by A sub 1. And let us call this as our first equation. Now, if we're going to consider the second condition, the other condition of the cylinder, where there is now applied load at the top of the piston. And let us show it again here, that case. So again, now we have here our piston, but it's applied with a force F, and due to this F, the elevation, or the difference in the elevation between this point, the base of the piston, and the liquid surface of the mercury, becomes 15 centimeters. So we would expect therefore that at this point, meron tayo ngayon ditong pressure, and let us call it, this pressure be defined as pressure sub 2, or P sub 2. And if you're going to apply the concept of the Pascal's law, we expect that at the same horizontal level, at the same point, so makatiwid at this point, on the tube, meron tayo ditong pressure P sub 2 also, where the pressure at the bottom, or at the base of the cylinder, can be taken as the ratio of the total weight acting at that piston, which is the sum of this weight and this F. So that you have here P sub 2, by applying again the Pascal's law, we expect that the P sub 2 nito ay equal dito sa P sub 2, di ba? Equal yan. And that this P sub 2 will be the ratio of the sum of this W and F divided by the cross-sectional area of this piston. So you have here W plus F over A sub 1. Samantalang dito naman, the pressure dito will be the product of the unit weight of the mercury multiplied by this H sub 2. And this will be equal to gamma multiplied by H sub 2. And from this relationship, we can express that W, which is equal to the product of gamma multiplied by H sub 2 multiplied by A sub 1 minus F. And let us call this as our second equation. Because we have here an equation that involves the weight of the piston, which are actually the same piston. So makatwid, we can equate this equation 1 and equation 2, so that this when equated, we shall have gamma H sub 1, A sub 1 be equal to gamma H sub 2, A sub 2 minus F. And because we are looking for this F, we can simplify the equation so that F becomes equal to gamma H sub 2 multiplied by A sub 1 minus gamma H sub 1 multiplied by A sub 1. So from here, we can factor out common terms. Gamma and A sub 1 are common in both terms. So we can factor out that, so that this equation for F becomes equal to the product of gamma multiplied by A sub 1 multiplied by the difference between H sub 2 and H sub 1. And if we are going to substitute those values of gamma, cross-sectional area, and the heights, therefore our F becomes equal to 13.55 represents our unit weight of the mercury at 20 degrees Celsius. This 9.81, when multiplied with this 9.81 becomes the unit weight of the mercury. We multiplied it by the area, which is equal to pi over 4 multiplied by 0.2 square, multiplied by the difference between 0.15 minus 0.025, and when we simplify the equation, this will result to a value of F equal to 0.522 kilonewton. So this is how we solve the problem, and we find that with this value of F, the elevation of the liquid, or the mercury, will rise to 15 centimeters above the bottom of the piston. Let us try to solve the second problem. The second problem states that the bottom of the river is 15 meters below the water surface, underneath which is a silt having a specific gravity of 1.75 and a thickness T. The pressure at the bottom of the silt is 500 kilopascal, and from here we are required to determine the thickness of the silt. For us to be able to understand the situation, let us try to draw the case or the problem. Okay, and imagine that the problem is something like this one. So in here we have here a liquid surface, liquid or the water, having a total height of 15 meters. And below this water meron tayong silt whose thickness is equal to T. And at the bottom of the silt is measured the pressure, and the magnitude is equal to 500 kilopascal. Okay, assuming that the specific gravity of the silt to be 1.75, we are required to find for this thickness. So let us try to identify in the problem the following given. Let's try to identify the following given. So we have here the following P sub 2 being equal to the product of gamma sub 1 multiplied by H sub 1 plus gamma sub 2 multiplied by H sub 2. That is simply the sum of the pressures exerted by the water and the silt. So in this problem, yung gamma sub 1 natin represents the unit weight of the water, and that is given at 9.81 kilonewton per cubic meter, while this gamma sub 2 represents the unit weight of the silt, and this is equal to 1.75 multiplied by the unit weight of the standard liquid, which is water. And if this will be substituted in this equation, then we can find that P sub 2 is equal to 9.81 multiplied by 15 plus 1.75 multiplied by 9.81 multiplied by the T representing the thickness of this silt. But it is given that the pressure at the bottom of the silt is 500 kilopascal representing P sub 2. That if this P sub 2 will be substituted to this equation, we can find for the value of T. So solving for T, therefore will be equal to following 500 minus 147.15 divided by 17.17, and T gives us a value of 20.55 meters. This becomes now the thickness of the silt, so that the pressure below the silt is equal to 500 kilopascal. So that's how we solve the second problem. Now let us move to the third problem. The third problem is somewhat the application of the variation of pressure, and the problem goes like this. So there is a piece of wood 50 millimeters square and 5 meters long, and weighing 550 kilograms per cubic meter, that is submerged vertically in the body of water. Its upper end being flush with the water surface. What vertical force is required to hold it in this position? So let us try to imagine our illustration. So in the problem, we have here a piece of wood having a cross section given to be 0.05 meters by 0.05 meters, representing 50 millimeter by 50 millimeter, and a height of 5 meters. This has a weight of 500 kilograms per cubic meter, lighter than the water. So if this will be placed in the water, we would expect that, assuming natin that this is here is the water, and if this will be placed in the water, because it is lighter than the water at 550, we would expect that this will float in this manner. But the problem states that the end of the wood is flush with the surface, and we need to push it down in order for this edge of the block to be flush with the water. There is a need for us to apply a force F here, a force F that will cause it to be flush in the water. So let us try to show what will happen if we force this with a force F. So the block will be flush with the water at that position. When the end of the block is at this position, the question is what F is needed to keep it in this position. So we will be finding for this magnitude of F that will keep the block of wood to be flush with the water on the upper edge. And how are we going to solve for the problem? Let us imagine that at this end of the block, the total distance from the liquid surface will be equal to 5 meters, representing the height of the block. So if we're going to consider, okay, the weight of the block be represented here by W, okay, therefore this W will be equal to the unit weight of the block multiplied by its volume. But we are given that, okay, the mass of the block is 550. So if we will be multiplying it by the gravitational acceleration, that is 9.81. Therefore, we shall be finding that the weight of the block will be equal to 550 multiplied by 9.81 Newton per kilogram multiplied by this volume, that is 0.05 multiplied by 5, representing the volume of the liquid. This gives us a total weight of 67.44 Newton, or if expressed in terms of kilonewton, this will be equal to 0.067 kilonewton, meaning this weight of the block is 0.067 kilonewton. And we expect that at the bottom of this block, there will be a force acting, and the direction is upward due to the hydrostatic pressure acting at the bottom. Okay, so if we will be solving for that P, this being the force acting at the bottom of the wood, this P would be equal to the pressure acting at this part multiplied by the cross-sectional area. But what is this pressure acting at the bottom of the block? This will be equal to the product of the unit weight of the block, the unit weight of the water, this one, because this is the water, multiplied by the height representing this 5 meters and the cross-sectional area. That if this will be substituted with its value, so we shall have 9.81 multiplied by 5 multiplied by 0.05 square, and this gives us a value of P equal to 0.12 kilonewton. After we have solved for this P and that of W, so we can now solve for this F. Since this is held in that position, meaning it is held in equilibrium, therefore it would satisfy the condition of equilibrium such that applying the condition of equilibrium, so summing up all the forces, vertical equal to 0, therefore and then assuming that upward force will be positive, then our equation becomes P minus this force applied minus this weight will be equal to 0. Since we have computed for this P and W, so we can solve for F, F being equal to the difference between P and W, and hence this will be equal to 0.12 minus 0.067 kilonewton, and therefore the value of F necessary to keep it in that position is equal to 0.053 kilonewton. And finally, the last problem that I have here is all about the application of the Boyle's law, applied to a diving bell. So in the problem we have here, a diving bell 4 meters high has the shape of a frustum of a circular cone with a closed flat top and an open bottom, having a diameters of 3 meters and 4 meters respectively. It is lowered from the outside air into the salt water, having specific gravity of 1.03 in an upright position. Question is, how deep below the water surface is the bottom of the diving bell when the water level is 2 meters in? So maybe we can understand the problem if we will be drawing our situation. Imagine natin that there is a bell, a frustum, in the form of a frustum of a right circular cone. At the top, it is given that the diving bell is 4 meters high, therefore the height of this diving bell is 4 meters, and has a closed flat top and an open at the bottom. This top is closed while this part is open. Having a diameter of 3 and 4 respectively, this upper part has a diameter of 3 meters, while the lower part of the frustum or the diving bell has a diameter of 4 meters. It is lowered from the outside air, meaning to say, initially this is exposed to an atmospheric pressure, and lowered into salt water. Let us imagine that there is our salt water whose specific gravity is 1.03, lowered until such time that the liquid surface is 2 meters above 2 meters inside the frustum. So let us try to again show the animation, and slowly let us try to look at what will happen inside the frustum as it is lowered below the water. Okay, as it is lower below the water, you would find that there are air, water getting inside of the frustrum until the height of the frustrum is 2.0. The question is, how much is this height? How much is this depth of the frustrum? See, when the height of the water inside is already 2 meters. Okay? So how are we going to solve for this problem? So from here, we will be applying the concept of the Boyle's law, which states that the pressure of a given quantity of gas varies inversely with its volume at constant temperature. So assuming that the temperature of this diving bell remains constant, as the liquid is compressed while it is immersed, while it is being submerged, then the pressure inside will vary inversely with the volume. Thus, we say that the product P1V1 is equal to P2V2. For in this law, we say that P1 is the absolute pressure at the initial volume of the air, and P2 is the absolute pressure at the final volume of the air. So what is that initial volume and what is this final volume? Yung initial volume na tinutukoy natin dito is when the frustrum is not yet submerged, while it is still in air. So you have the initial volume, and the absolute pressure is this atmospheric pressure. Okay? While the P sub 2 is the pressure when it is already submerged, so that the volume of the air is when there is already 2 meters of water inside the vessel. This becomes our V sub 2, and the pressure would be the pressure inside this vessel. So how do we get therefore our values? So let us try to imagine analyzing the properties of the gas inside the diving bell before and after being submerged in water. So let us have our illustration again while the bell is not submerged yet. So before the bell is submerged, we have here our vessel, an open frustrum of the cone having a height equal to 4, a diameter at the base equal to 4, and the diameter at the top which is equal to 3. So we expect here that our pressure is the atmospheric pressure, hence this will be equal to 101.3 if that would be the absolute. Okay, so our V sub 1 represents the volume of the cone initially, and this is equal to, if we're going to recall our formula for the volume of the cone, which is equal to pi multiplied by h over 3 multiplied by the quantity capital R square plus RR minus the small r square, where in here yung capital R natin represents the radius of the larger base, the radius of this base, and the small r represents the radius of the smaller base, this base. That if you're given the diameter of 4 and 3 respectively, therefore our radius becomes 2 and 1.5, which when substituted here in the formula, our volume of the cone initially when it is not yet submerged in water will be equal to pi multiplied by 4. This is the height of this frustrum, divided by 3 multiplied by 2 square plus 2.2 multiplied by 1.5 plus 1.5. That when this is simplified, our initial volume will be equal to 38.75 cubic meters. So this will be our V sub 1. Now when the well is submerged in the liquid, when the bell is already under the water, what happens now? It is the situation when the bell is already inside or under the water. There is already 2 meters water inside the bell, and hence our height of the air will be the remaining, which is also 2 meters, because the total height of this bell is equal to 4 meters. The diameter of the bell remains at the top at 3.0 meter, while the diameter at this part of this bell, which is halfway from the top and the bottom, and therefore this diameter will be equal to 3.5. And if we are to recall the formula again for the volume of this frustrum will be equal to pi times h over 3 multiplied by r square plus the product of rr plus the product of the small r square. So when this is substituted with the value, our volume will be equal to pi multiplied by 2 divided by 3 multiplied by the quantity 1.75 square plus the quantity 1.75 multiplied by 1.5 plus 1.5 square, which when simplified, our final volume is equal to 16.62 cubic meter. This is our volume then. Okay, and if we're going to solve for P sub 2, then we apply the principle of the Boyle's law, which says that the product of P1 V1 is equal to P2 V2. Okay, substituting our values here, our P1 is equal to 101.3. Okay, with the volume equal to 38.75, and P sub 2, which is the unknown, the volume, while it is now immersed. With the volume equal to 16.62 cubic meter, our P sub 2 becomes 236.184 kilopascal. This now becomes the pressure of the vessel inside, or the prostrum inside, which is acting all the way, all throughout the surface of the prostrum, including this part of the water. Because this part of the water is now subjected to 234.184, we expect that all throughout this level, considering the principle of the Pascal's law, this horizontal level, the orange one, will be subjected to the same pressure of 236.184 kilopascal. And with this being the pressure at this point of the liquid, we can now find for the magnitude of the depth, because this distance will be equal to depth over 2. This is the pressure at the distance d minus 2 from the liquid surface. Hence, substituting in the solving for the depth of water at the level of the base of the diving bell. So we shall be getting the value of the pressure using the variation of the pressure, that P sub 2 representing the pressure at this point being equal to P sub 1, which is the pressure at the atmospheric at the atmosphere, plus rho gh, or P sub 1 plus gamma multiplied by h. Kung saan itong P1 natin is the atmospheric pressure, which is represented here, equal to 101.3. This is the pressure at the surface. Our rho represents here the density of the seawater, and g is the acceleration due to gravity, which when substituted, this will be equal to 1.03 multiplied by 9.81. While this one is the depth of the water, or the distance from the water surface to this part of this prostrum at a depth equal to d minus t. So when substituted with the value, including the value P that is computed at 236.184, then our equation becomes 236.184 plus 101.3 plus the product of 1.03 times 9.81 multiplied by d minus 2. And when this is simplified, we can solve for the d. D becomes equal to 15.35 meters, meaning at a depth d equal to 15.35, the distance from the bottom of this diving bell. The pressure inside is 236.184, and there is a height of 2 meters inside that diving bell. Sana ay nakatulong sa inyo itong ating solution sa mga problems, para lalo nyo maintindihan ang applications ng Pascal's law, ng Boyle's law, at ang solutions to any problems that deals with the variations of pressure. Once again, thank you very much for watching.